I'd like to get back into making videos in general, so I'm going to recklessly promise the contents of my next one. Next time on this channel, I'll be giving a good explanation of planar ternary rings.
Well, I guess I'm one of those guys. Anyway, planar ternary rings are what this video is about. Unfortunately, they fall into an intersection of being both kind of complicated and very abstract, which will make giving a good explanation more difficult. So, let's punt on that one for a moment and do some fun geometry puzzles instead. Here's the setup. We're in the plane and we're given 3 points, 0, 0, 1, 0, and 0, 1. We're allowed to do 3 constructions: the line joining 2 points, the point where 2 lines meet, and the parallel to a line through a point. The puzzle is to figure out how much stuff we can construct with only these things. I figure we'll do like 4 of these real quick and then get back to the ternary rings. So first up, given 2 points on the x-axis, call them x0 and y0, construct xy. This one's pretty straightforward. We just need to construct a special line first. To do this, we make the 2 axes by joining the origin to the other 2 points. Then we make a vertical line at 1, 0 and a horizontal line at 0, 1 using the parallel construction. Since these lines are not parallel, they meet at a point, namely 1, 1. Then the line joining 0, 0 to 1, 1 is the line where both coordinates match, which I will call the identity line. Now this is a powerful line. Constructing a vertical line through y0, we get a line that meets the identity line at the point yy. The horizontal through yy meets the vertical through x0 at the desired point xy. Great! We also have a pretty clear way to reverse this too, which will be useful in the next couple puzzles. Speaking of, here's the second puzzle. Given x0 and y0, construct x plus y 0. So, we're doing addition now. There are actually a couple ways we could do this. I'll show the one that uses the identity line in the clearest way. As before, construct yy and then use a horizontal line to make 0y. When we construct the line parallel to the identity line through 0y, this has the effect of essentially translating the identity line upward. Then, the vertical through x0 intersects this translated line at x plus y. From there, we can get x plus y0 out by doing the reverse thing I mentioned earlier. Alright, on to the third. Given x0 and y0, construct x times y0. We did addition, now we're doing multiplication. Construct the point 1y and make a line through it and the origin. The vertical through x0 meets the line at xy. Finally, we project down to xy0 as before. Before we do the last puzzle, we should probably prove that these constructions actually work. To do this, recall that every line in the plane is given by an equation. For vertical lines, it's x equals a for some a, and for all other lines, it's y equals mx plus b for some slope m and some y-intercept b. For simplicity, denote these two kinds of lines by bracket a and bracket mb, where the brackets distinguish them from points xy. So the horizontal axis is bracket 0, 0, the vertical axis is bracket 0, and our identity line is bracket 1, 0. 2 lines are parallel if they're either both vertical or they have the same slope. All our constructions can then be done in numbers. We'll go in reverse order from earlier, starting with the parallel to a line through a point. Call the point xy. If the line is vertical, then bracket x works. So suppose we have some other line bracket mb. We already know the desired line has slope m, so we want to find some mystery intercept b'. We're just solving the equation y equals mx plus b' for b', which we can do with a simple subtraction. Thus, the desired line is bracket m y minus mx. Second, we want the point where 2 non-parallel lines meet. If one of the lines is vertical, then the intersection is straightforward. Bracket mb and bracket a meet at a ma plus b. Otherwise, to find the intersection of bracket mb and bracket m' b', where m and m' are different, we solve the equations y equals mx plus b and y equals m'x plus b' for x and y. Doing this is just a bit of algebra, which gives b' minus b over m minus m', mb' minus m'b over m minus m' as the desired point. Finally, we want the line joining 2 points, say xy and x'y'. If x equals x', then bracket x is incident with both points. Otherwise, the slope is given by rise over run, and we can reuse the parallel construction from earlier to get the intercept. Simplifying this gives the line y minus y prime over x minus x prime, xy prime minus x prime y over x minus x prime. Proving that our constructions work for coordinates, addition, and multiplication then just amounts to a bunch of calculations. I'll spare you the details and move on to the last and perhaps easiest of our 4 puzzles. Given points x0, m0, and b0, construct mx plus b 0. It's literally just doing addition and multiplication at the same time. In principle, we could just put our constructions from earlier together, but it happens that there's actually a better way. After all, if we construct the line bracket mb, then we just need to intersect it with bracket x to get the point x mx plus b. Doing this isn't too hard. Start by constructing 1m and 0b. Using these, join 0, 0 to 1m to form bracket m0, and form bracket mb using the parallel construction. One intersection and a cleanup later, we're done. So that was fun. Using the real numbers, which carry the operations of addition and multiplication, you can construct a geometry of points and lines which carries its own set of operations related to which lines pass through which points. Then, using the geometry of points and lines and the triangle 0, 0, 1, 0, 0, 1, you can essentially recreate the original algebraic operations on the line bracket 0, 0. A good time was had by all. Let's return to the topic of the video. Planar ternary rings, or PTRs for short, are a class of algebraic structures. They consist of a set R with the ternary operation T and 2 constants 0 and 1, all of which satisfy 5 axioms. For the particular phrasing of the axioms, I'll be drawing from Charles Weibull's Survey of Non-Desarguesian Planes. As it happens, the real numbers are an example of a PTR with the operation T of ABC equals A times B plus C. That'll be worth keeping in mind as we go through the axioms. The first 2 are basically just equations which make 0 and 1 behave as identities. These follow immediately in the case of the real numbers. The remaining 3 axioms describe properties of negation and division in a very general way. For any algebraists in the audience, it's worth noting that the planar ternary rings are more closely related to fields than to rings. For that reason, they're sometimes called ternary fields. The third axiom says, for all elements a, b, and c in the set R, the equation T of ABY equals C has a unique solution y in R. In the real numbers, we write this as A times B plus y equals C. This seems a lot like the equation y equals xm plus b, just with different letters. This is no coincidence. We've actually already proven that the real numbers have this property. It just amounts to saying that given a point AC and a slope b, there is a unique line with slope b passing through AC. Y is just the y-intercept of that line. The fourth axiom says, for all A prime, B, and B prime in R, where A and A prime are different, the equation T of xAB equals T of xA prime B prime has a unique solution x. In the real numbers, this is also something we've already seen. 2 lines, bracket AB and bracket A prime B prime, with different slopes, intersect at a unique point x, xa plus b. We even found a formula for x earlier. With these new letters, we get x equals b prime minus b over a minus a prime. You've probably already guessed it, but the fifth axiom follows the same trend. For all A prime, B, and B prime in R, where A and A prime are different, the equations T of AXY equals B and T of A prime xy equals B prime have a unique solution xy in R. In the reals, this says that between points AB and A prime B prime, there's a unique line bracket xy. In particular, this is the line B minus B prime over A minus A prime, AB prime minus A prime B over A minus A prime. There's a lot to unpack there. We have a list of axioms for an algebraic structure, but in the case of the real numbers, all the axioms seem oddly related to coordinate geometry. That's weird. More weird, though, is the fact that we started with a ternary operation in the first place. Like, in the real numbers, we build the ternary operation out of 2 binary operations. Addition and multiplication are easier to work with than this ternary thing. For that matter, we can even split t back into addition and multiplication. Define two operations, x plus y equals t of x1y, and x times y equals t of xy0. Since we can always do this, it seems like we don't get anything from the ternary operation in the first place. However, looks can be deceiving. See, in the general case, we actually lose something if we split t into two operations like that. In the reals, we can get t back by recombining the operations using the identity t of abc equals t of ab0, 1c. However, this doesn't work in general, and I can prove it. It'll just take a while. First, we'll ruin multiplication. Define a new operation on the real numbers called Moulton multiplication, read as a Moulton b, that's a times b if at least one of a or b is positive. Otherwise, when both a and b are negative, a Moulton b equals half of a times b. To see how this works, drawing a picture will be useful. Here's the function x Moulton m for a constant m, which I'll adjust up and down for demonstration. When m is positive, we get a normal line. When it's negative, we get a little corner at 0, and the function droops down on the left instead of continuing the line on the right. More generally, any function of the form y equals x Moulton m plus b gives rise to a sort of Moulton line, which is like a line, but with a little corner in the middle sometimes. You may have noticed, but this Moulton operation is a lot worse than normal multiplication. For instance, it doesn't distribute over addition. It's not so bad, though, that the reals together with the operation t of abc equals a Moulton b plus c don't form a ternary ring. 0 and 1 behave normally, which takes care of the first two axioms. For the third, it's clear visually that if we have a point and a Moulton line not on it, we can just shift the figure up to the point. Algebraically, we can say that if either a or b is positive, then we can use the parallel line formula from before, and if they're both negative, we can just include a factor of 1/2. The other two constructions aren't as convenient to do algebraically, so we'll stick to pictures for our proofs. The fourth axiom, rephrased geometrically, says that if two Moulton lines have different slopes, then they must intersect. If both slopes are positive, then this is just the usual result for normal lines. If one line is positive and the other negative, then it's clear that since one goes up and the other goes down, they'll have to meet somewhere. The case where both are negative is the tricky one, but it's not so bad. Suppose the two Moulton lines don't intersect on the right side of their corners. Then, if they didn't droop, then they would intersect on the left. Let's draw a triangle using the point where they would meet and the two y-intercepts. If we stretch the triangle horizontally by a factor of 2, then we get two lines which match our Moulton lines on the left side of the y-axis, and which clearly intersect since stretching just moved the intersection point over. So we know the fourth axiom holds even if we don't have a formula. Finally, the fifth axiom is the one that says there's a Moulton line between 2 points. For this one, I'll just appeal to the fact that Moulton multiplication is continuous. Pick two Moulton lines through one of the points such that they meet the vertical through the other point above and below it. This is just a matter of picking a big positive slope and a big negative slope. Then, as we continuously go from one slope to the other, we need to pass through the point because of the intermediate value theorem. This explanation is admittedly more of a sketch than a proof, so I'd recommend thinking about how you'd formalize it yourself. Regardless, a Moulton b plus c gives a planar ternary ring. So what? What we wanted was a PTR which doesn't just boil down to a pair of operations, but x plus y and x Moulton y are not that. Where's the PTR that doesn't satisfy that one identity from earlier? The trick is to play the same game from the start of the video, but with a twist. Instead of using normal lines, we'll use Moulton lines, and further, we'll flip them sideways. Before we do that, though, we'll review the insights from the game. Earlier, we saw that this diagram can be used to extract the operation xm plus b using only constructions on points and lines. Similarly, if we draw the same diagram with Moulton lines, then we can retrieve a different operation, namely x Moulton m plus b. In both cases, we have points, a kind of lines, and a triangle, and from these things we're able to extract an algebraic operation. So what do I mean when I say we'll flip the Moulton line sideways? Well, consider a Moulton line through 0, 0, specifically one of the ones with negative slope, which droops by a factor of 1/2 on the left side. What happens if we flip it over the identity line? Well, it happens that we get another Moulton line. The left-hand part of the line is now on the right, but the factor of 1/2 becomes a factor of 2 because of the reflection. When a Moulton line does not pass through the origin, though, the story is a little different. On a normal Moulton line, the little corner is always on the y-axis. On a sideways Moulton line, the corner winds up on the x-axis instead. So, when we construct the parallel to a Moulton line through a point, it's less like we're shifting up and down to meet the point, and more like we're shifting left and right. It's pretty weird, which is good because we're trying to construct something weird. Let's work through a calculation with this new kind of line. Suppose we want to find t of 2, -1, 2. First, we form the sideways Moulton line between 0, 0 and -1, 1. Then, we shift it over so that it passes through 0, 1. This line intersects the vertical through 2, 0 at 2, 1, so t of 2, -1, 2 is 1. Notice that for non-sideways Moulton lines, the weirdness was always on the left side of the y-axis, but now the corner can move left and right. Now another calculation. What's t of 2, -1, 0? -1 is the same slope as before, so we start with the same line through 0, 0. Then we don't shift the line over, so 2 is on the right side of the corner and we get the normal answer, -2. How about t of -2, 1, 2? Well, this has a positive slope, so all the lines we deal with don't even have corners, and we get 0. Notice what just happened. T of 2, -1, 2 is 1, but t of 2, -1, 0, 1, 2 is 0. This sideways Moulton operation doesn't satisfy the identity that would allow us to recover it from a pair of binary operations. In fact, it happens to be the case that t of xy0 is x Moulton y, and t of x1y is x plus y, which demonstrates that what we recover is different from what we started with. It's not a full counterexample, though, until we show that it's a planar ternary ring. In principle, this wouldn't be that much harder than showing that A Moulton B plus C was a PTR. Heck, we could even write out an expression for the operation. Instead of doing that, though, I want to do something way more powerful. Suppose we have some planar ternary ring R with constants 0 and 1 and an operation T. This could be the real numbers, or either of the Moulton operations from before, or any other PTR. In all the examples we've seen so far, it's possible to construct a sort of point line geometry from R, and then, more shockingly, recover the operation T from the geometry. Is this always possible? And what can we say in general about these point line geometries? Well, in all the cases we've seen so far, the construction of the geometry has been the same. First, we have a set of points, which consists of pairs of elements x, y from the set R. Then, we have a set of lines, which come in two flavors, vertical lines bracket A and non-vertical lines bracket MB. Between the set of points and the set of lines, we have a relation which says something like, this point is on this line, or equivalently, this line passes through this point. This relation is called incidence and is denoted with this symbol, though we shouldn't confuse point line incidence with set membership. So, we say the point xy is incident with bracket A if x equals A, and xy is incident with bracket MB if y equals t of xmb. The first two PTR axioms tell us some things about the structure immediately. Since A equals both t of 1a0 and t of a10, we have that the point 1a is incident with the line bracket a0, and aa is incident with bracket 10. So the points on bracket 1 correspond to the slopes of the lines through 0, 0, and bracket 10 is the identity line as before. Similarly, since c equals both t of a0c and t of 0ac, we have that the point ac is on the line bracket 0c and 0c is on bracket ac. So the lines with slope 0 are the horizontal lines, and the y-intercept behaves as expected. The other three PTR axioms tell us more about this incidence geometry we've constructed. Specifically, they give it the structure of what's called an affine plane. Let's see what that means. An affine plane is a kind of incidence geometry, that is, a set of points, a set of lines, and a relation between them called incidence, which satisfies three axioms. For the particular phrasing of the axioms, I'll be drawing from Burkert-Polster's A Geometrical Picture Book, specifically Chapter 1.3. Fun fact, Polster is actually the guy from the Mathologer channel. Small world, right? The first axiom says that two distinct points are contained in a unique line. This corresponds to the fifth PTR axiom in a nice way. Let's rephrase it in terms of incidence. Given 2 points, a, b, and a prime, b prime, with a and a prime different, there's a unique line, bracket xy, which is incident with both. This almost entirely covers the first affine plane axiom. We just need to take care of a few cases. Since a is not equal to a prime, the 2 points cannot both lie on a vertical line. After all, the only vertical through AB is bracket A, and A prime B prime is not incident with that line. If it were the case that A equaled A prime, then the only line between them would be the vertical line bracket A, since a non-vertical line bracket MB can only share 1 point with a vertical line bracket X, namely T xMB. The second axiom says, given a line and a point, there is a unique line through that point that is parallel to the given line. Here, the word parallel means exactly what it means in ordinary geometry. 2 lines are parallel if they are either the same line or there is no point which is incident with both. This property of affine planes corresponds to the third and fourth axioms of PTRs. In incidence terms, the third axiom says that given a point CA and a line bracket BX, there's a unique line bracket BY through CA. The fourth says that given lines bracket AB and bracket A prime B prime, whose slopes differ, there's a unique point X, T xAB, which lies on both. The latter tells us that if 2 lines have different slopes, then they aren't parallel, and the former tells that if 2 lines have the same slope, then they are parallel. The third and final affine plane axiom says that there exist 3 points which are not all incident with a common line, essentially that there exists a triangle. This is the easiest to show since we can just use the points 0, 0, 1, 0, and 0, 1. The only line through 0, 0 and 0, 1 is bracket 0, and 1, 0 isn't on that line. Granted, this assumes that 0 and 1 are different, which wasn't one of our PTR axioms. If 0 equals 1, though, then we have that x equals t of x1, 0, which equals t of x0, 0, which equals 0 for all x. So that structure is trivial anyway. Thus, the incidence geometry derived from a planar ternary ring R is an affine plane with a choice of triangle 0, 0, 1, 0, 0, 1, which can be used to extract the original operation from R. The real numbers give rise to what's called the real affine plane, which is what you get if you take the Euclidean plane and throw away everything except for points and lines. The Moulton PTR from earlier gives an incident structure called the Moulton plane, which is named after an astronomer who has a moon crater named after him. In order to understand why the Sideways Moulton structure gives a PTR, it suffices to show that any triangle in any affine plane gives rise to a PTR. To see this, suppose we have an affine plane with some triangles whose vertices all suggestively call 0, 1, and 1 prime. Let R denote the set of points incident with the line 0, 1, which is uniquely specified by the first affine plane axiom. Call the lines parallel to 0, 1 prime vertical and the lines parallel to 0, 1 horizontal. Then the vertical and horizontal lines through 1 and 1 prime respectively intersect at some point. Call it I. The line 0i will be our identity line. From here, as you might have guessed, all of the points in the plane can be given coordinates in R by projecting a vertical down to 0, 1 and a horizontal over to 0i and then down to 0, 1. By construction, the points 0, 1, and 1 prime are given coordinates 0, 0, 1, 0, and 0, 1. We also coordinatize the lines. Verticals are labeled with the point at which they meet 0, 1. Every other line L can be represented using a pair of points in R. Since L is not vertical, it must meet 0, 1 prime at some point, which can be projected over to 0i and then down into R. L must be parallel to some line through 0, and that line must intersect the vertical through 1 at some point, which can be projected over to 0i and then down. Thus, non-vertical lines are also coordinatized by pairs of elements of R. Lines will, of course, be written with brackets. Finally, we define T of xMB. take the intersection of the vertical labeled bracket x and the line labeled bracket mb. Project over to 0i and down to r. That's t of x mb. That r together with 0, 1, and t form a planar ternary ring follows from the same correspondence of axioms that showed that any PTR gives rise to an affine plane. The first two are equivalent to the incidences 1a is on bracket a0, aa is on bracket 10, AC is on bracket 0c, and 0c is on bracket AC, all of which follow from the way in which points and lines were given coordinates. Then, the third and fourth PTR axioms follow from the parallel axiom in affine planes, and the fifth PTR axiom follows from the fact that any two distinct points have a unique line between them. So, to summarize, the operation A Moulton B plus C gives a PTR. The PTR gives the Moulton plane with triangle 0, 0, 1, 0, and 0, 1. Since any triangle in any affine plane gives rise to a PTR, if we pick the triangle 0, 0, 0, 1, and 1, 0, which is the same but with the second and third vertices swapped, we can construct a PTR. However, since the vertices are different, this gives a different algebra. In fact, swapping the vertices is equivalent to flipping all the lines sideways, so the resulting algebra is the Sideways Moulton operation, which must therefore be a ternary ring. Ordinarily, that would be a nice place to stop. Like, we've come full circle, we found this neat algebra geometry correspondence, a good time was had by all. However, before you go, I want to show you some finite affine planes and their corresponding algebras, just so you don't go away thinking that all geometry is just the real numbers and, like, the real numbers after a car accident. Our first example is the complete graph on 4 points. No, really. If we take the vertices as points and the edges as lines, with the obvious incidence relation, that's an affine plane. Think about it. An edge in a graph is a set of 2 points. Since the graph is complete, every 2 points have an edge between them. By definition, 2 edges are parallel if they're equal or disjoint, and in particular, each edge has a unique other edge to which it is disjoint. So the complete graph of order 4 is basically the smallest affine plane possible. So what about the algebra? Well, I'll spare you the details, but every choice of triangle gives rise to a PTR isomorphic to this. As it happens, this one can be split into 2 binary operations, which look like this. If any algebraists are still in the audience, you'll recognize this as F2, the field of order 2. Indeed, if F is a field, then the operation xm plus b is a ternary ring. That means the complex numbers also form a PTR and an affine plane. Even some more exotic structures like the quaternions and the octonions have enough nice division properties to get affine planes. Anyway, let's look at the next smallest field, which is isomorphic to the integers mod 3. What does this one's affine plane look like? Well, it'll have 9 points which we can arrange into a grid. The horizontal and vertical lines are pretty straightforward, so I'll draw those in. Next, we have the lines with slope 1. The first of these is easy since it's just a diagonal, but what about the parallel to the point immediately above it? Well, it should pass through these 3 points, which are definitely not collinear in the picture. That isn't an issue, though, since we can just bend this line around to meet the point in the corner. Same goes for the other parallel. I'll stick to clockwise for consistency. Since 2 equals -1, mod 3, the other diagonal winds up being a line with slope 2. Then, the other 2 lines can be drawn by bending around as before. That's neat, right? I don't really have much to say about it, but it's conveniently small, pretty in a symmetric way, and completely alien to the kind of geometry we're used to. For the other prime finite fields, it's actually not too bad to get a computer to draw them. Like, here's 2 lines in the affine plane that comes from the field with 97 elements in Desmos. There's a link to that in the description. Back to small stuff, though. What about the field on 4 elements? For the non-algebraists in the audience, this is not the ring of integers mod 4. Instead, it's more like the complex numbers. You start with F2, which is isomorphic to the integers mod 2, and you adjoin an element I, which satisfies the equation I squared equals I plus 1. The resulting addition and multiplication tables look like this, but what does the affine plane look like? Well, chapter 9.2 of Polster's picture book has an absolutely wild answer for us. Draw a regular pentagon. Now, draw a star on these 5 vertices and mark the points where the segments intersect. This forms a smaller pentagon on which we draw another star and 5 more points. In the middle of all this, we draw a single star and then erase all the segments. So 16 is the correct number of points, but you've probably noticed that this isn't a grid. Like, I struggle to imagine something that is less of a grid than this. However, what this arrangement lacks in gridliness, it makes up for in rotational symmetry, and therein lies a clever trick. See, if we draw a line like this, then we can rotate it around to get 4 other lines. So, while there are 20 lines in this plane, we only need to draw 4, and the rotation strat takes care of the rest. Polster gives a parallel class of 4 lines, this vertical-looking one, these 2 horizontal ones, and a bendy guy like the ones we saw in order 3. If we draw all the rotations in too, we get this picture, which looks like we're about to summon something. Isn't that great? It's really good, I think. There's lots more you can say about this stuff, but I think that's enough for one video. I've learned my lesson, definitely never making any promises ever again. Let's just make sure I've covered everything.
Next time on this channel, I'll be giving a good explanation of planar ternary rings and what they have to do with projective planes
Wait, projective planes? Hold on,